Hey guys, welcome back to General Chemistry. Today we're going to talk about something called Lewis structures. So up until this point, we have put the molecules into two categories, ionic or covalent. And today we're going to focus on covalent molecules. So what do those electrons look like in a covalent molecule? Just as a reminder, the difference between ionic and covalent. So ionic was a metal bound to a nonmetal, and here electrons were transferred. So this is where we talked about somebody gives an electron away, somebody steals an electron. Here we had to worry about charges, right? So if I change the number of electrons, that's going to cause a charged particle, ions, and those charged particles are attracted to one another. So that's an ionic bond. In covalent bonding, we've got a nonmetal bound to a nonmetal, and here electrons are shared. So no longer are we worried about charges and having a neutral molecule. Now we can really put together any combination of nonmetals and make a covalent molecule. So what we're going to take a closer look at is how exactly those electrons are shared and then some characteristics of sharing electrons. So when we draw covalent molecules, we typically represent the valence electrons as dots. And so this is what we call a Lewis structure. So it focuses on the valence electrons in such a way that we draw them around the atom as a dot. So what we typically do is we will draw the chemical symbol. So in this case, we've got oxygen. Then we think about kind of an imaginary box around this oxygen. So if I put a box around this atom, then we can represent valence electrons, and we typically do 2 electrons on each side of the box. So looking at our periodic table, we see that oxygen is in group 16 or 6A, so that's how I predict that it has 6 valence electrons. And then to represent those valence electrons, I just do 1, 2, 3, 4, 5, 6. Okay, so up to 2 electrons can go on each side of the box until we reach the full number of electrons. Now, there is a difference between the one that I drew and the one that's depicted on the slide here. So here I did 2, 2, 2. On the slide, they did 2, 2, 1, and 1. It does not matter. Both of those will get you to the same answer ultimately. So I'm not going to split hairs over which way we do it. Really, the only take home here is imaginary box around the chemical symbol, up to 2 electrons on each side. So let's try a couple. So if I were to do the Lewis dot structure for bromine, I would start by writing the chemical symbol. So chemical symbol for bromine is Br. I look at the periodic table. I see that bromine is in 17 or 7A. So it's got 7 valence electrons. So I'm going to depict it like this. 1, 2, 3, 4, 5, 6, and 7. Again, it doesn't matter what side of the box you start on. It doesn't matter where that 1 electron is by itself. It's on the top or the bottom, the left or the right. What I'm looking for here is 7 electrons around that atom. So why don't you go ahead and pause the video and see if you can do the Lewis dot structure for argon. All right, so argon, the chemical symbol is Ar. Looking at the periodic table, argon is one of our noble gases, so it has 8 valence electrons. So I'm just going to draw 1, 2, 3, 4, 5, 6, 7, and 8. Mix it up a little bit on this one. I drew X's instead of dots. What I'm trying to get at here is I don't really care what you draw around that atom, as long as there's 8 of them around argon. So it could be dots, it could be X's, it could be smiley faces or sailboats, whatever you want, as long as there's 8 around there. Okay. So Lewis dot structures are going to lead us to how these covalent molecules share electrons. Before we dive into a full-blown Lewis dot structure for a molecule, I want to talk just about I want to talk about some like rules that we have to follow or things we have to think about as we're drawing Lewis structures. So the first rule that I want to talk about is something called the Octet Rule. So the Octet Rule says that to have 8 electrons in the valence shell makes atoms particularly stable. So here we see one of our noble gases. We see neon. Neon is a noble gas. It's a particularly stable element. All of the noble gases are. And now we know what makes them particularly stable is having those 8 electrons in the valence shell. And sometimes we refer to this as a full valence shell, so 8 meaning full. In this chapter, you'll see there's something magical about the number 8. So as these atoms start sharing electrons, the whole purpose of the exercise, the whole reason that they're doing that is to have an octet, to have 8 in the valence shell. Now, there's always exceptions to the rule. So if you guys look at your periodic table, you'll see that helium is stacked on the noble gases. So he's in the family of noble gases. But if we look at the electron configuration for helium, one of the things we'll notice is it does not have 8 electrons in the valence shell. It has 2. So helium is an exception to the rule. So it's stacked on the noble gases because it behaves like them. It's particularly stable. It's a gas at room temperature. Doesn't really react with anything else. But it's an exception because it is happy with a duet. So having 2 electrons in the valence shell. So with this exception to the rule, there's going to be some other guys that also are the exception. So if you look at the atoms that I put in here, included them as the exception, they're all atoms that are very close to helium. So just before it or just behind it. The one exception, the one that you're really going to have to know and understand really is hydrogen. So as we start to build these Lewis structures, every other atom is going to strive for 8 electrons in the valence shell with the exception of hydrogen. Hydrogen's going to be okay with just 2. So hydrogen will want a duet, 2 electrons. Every other atom that we deal with will want 8. Okay, so let's dive into a Lewis structure. Really the best way to do this is to walk you through a Lewis structure, and then we'll go back and explain some of the things that I did. So I'm going to draw the Lewis structure for water. So water is H2O. Okay. So the first thing that we're going to do for any Lewis structure is we're first going to just tally or gather all of the valence electrons that are brought to the party. So what I'm going to do here is I'm going to look at hydrogen, and I've got 2 of those, and oxygen. And I'm just going to add up how many valence electrons each of these atoms have, just so I know how many I'm dealing with. So if we look at hydrogen, it's in group 1A, so he brings 1. The other hydrogen brings 1, and oxygen brings 6. So adding these together, I've got 8 valence electrons at my disposal, or 8 valence electrons that I'm going to use to share amongst these guys. The next thing that we're going to do is draw what I call a skeletal structure. So start to think about how these atoms might be arranged, how they might be connected to one another. And a good rule of thumb here is think symmetry, think symmetrical. So here I've got 2 hydrogens. I have 1 oxygen. So I'm going to put the oxygen in the middle, and very symmetrically, I'm going to put a hydrogen on either side. So that's a general rule of thumb is they like to have balance. They like to have symmetry. So that was step 2, draw the skeletal structure. Step 3 is to start giving electrons to each atom to fulfill these octets, or in hydrogen's case, the duet. So start putting electrons on the paper. So the first thing I'm going to start with is I'm going to draw 2 electrons between the hydrogen and the oxygen. So in this case, these two electrons are being shared between hydrogen and oxygen. So oxygen is touching these two electrons and hydrogen is touching these two electrons. So those are being shared between those two atoms. And then I'm going to do the same thing on the other side. So I'm going to draw two electrons between that hydrogen and oxygen. So again, they're sharing those electrons. Now, I had 8 valence electrons at my disposal. I've put 4 onto the board. So I put 1, 2, 3, 4 onto the board. I still need to find a home for 4 more electrons. So I can start to look at where these electrons are. So over here, we've got this hydrogen is touching 2 electrons. And remember, hydrogen is happy with a duet. He's happy with touching 2. So I'm not going to give that hydrogen any more electrons. And same thing over here. This hydrogen is touching 2 electrons. He's good with that. He doesn't want any more. But if I look at oxygen, he's touching 1, 2, 3, 4 electrons, and that's not enough. He wants to touch 8. Well, good news is I have 4 more electrons to find a home for. So I have 4 on the paper, and we're going to go 5, 6, 7, 8. Okay. I have 8 electrons at my disposal, and I've used 8. I'm done. I can't add any more. I've used every single one, so that's kind of the stopping point. Now we need to assess it. So the whole purpose of the exercise is to fill valence shells. So again, if I look at this hydrogen, he is touching 1, 2 electrons, and he's happy with that. That's a full valence shell for him. This hydrogen over here is touching 1, 2 electrons. That's a full valence shell. He's happy with that. And then if I look at this oxygen, he's touching 1, 2, 3, 4, 5, 6, 7, 8. And that's exactly what he wants. He wants to touch 8 electrons. That would be a full valence shell for him. So this is the Lewis dot structure for water, depicting 8 electrons being shared amongst these atoms, and they're filling those valence shells are filling those octets. So now some terminology. Let me get my mess out of the way and depict this a little bit better. So just some terminology to get out of the way. We've got bonding pairs and lone pairs. So bonding pairs are going to be pairs of electrons that are shared between 2 atoms. So here we've got a bonding pair shared between hydrogen and oxygen. Here we have a bonding pair shared between oxygen and hydrogen. So these bonding pairs are shared between 2 atoms. Lone pairs are going to be non-bonding. So these are going to be pairs of electrons that belong to just one atom. So if I see these 2 electrons up here at the top, those are a lone pair that belong to oxygen. And down here, we see another lone pair that also belongs to oxygen. The reason I take time to talk about this terminology is when we take these Lewis structures from 2-dimensional into 3 dimensions, understanding how many bonding and lone pairs there are is going to set you up for success to predict the 3-dimension shape. So it's important that we start thinking about it now. The last thing I want to talk about on this slide is this idea of a bonding pair. So quite often, bonding pairs are not depicted as dots between 2 atoms. Quite often, bonding pairs are depicted as straight lines. So if I were to label this, that line right there is also a bonding pair. And the important thing to note, if you do in fact use the lines, and we are lazy chemists, so lines are easier than dots. If you do, in fact, use the line, you just have to remember that this line represents 2 electrons. So that's just going to be the big take home there. If I do a bonding pair, I just need to make sure I count 1, 2 when I'm tallying up the electrons. So in conclusion, here were the steps that I used, and we'll do more examples in later videos. But here were the steps that I used. So number one was to calculate the total number of valence electrons. So just think about these atoms as coming to a party and throwing their electrons into a cooler, much like you would throw beverages into a cooler at a party. We just toss them in and then distribute from there. Number two is to write the correct skeletal structure. The more you do these, the more comfortable this will get. Just some helpful hints here is try a symmetrical approach. So if there's 3 of a particular atom, those are probably going to be around a different atom. So think symmetry. And hydrogen will always be terminal. So you'll never see a hydrogen like in the middle of a compound because it's touching too many electrons. So hydrogens will always be terminal. They'll always be on the outside. So 2 helpful hints there. After you have the skeletal structure, then you can distribute electrons, filling as many octets as possible. So I like to start with bonding pairs and then give out lone pairs from there. And then we'll talk more about this in a different video, but if you do steps 1 through 3, you don't have any more electrons to distribute, and somebody lacks an octet, then you can explore something called a double or a triple bond. But again, more on that in the future. So that's it for Lewis structures. That's your introduction to Lewis structures. I hope you guys found this helpful.